So, good evening, everyone. So, today, as first session, Dr. Biswarup Rana will give his valuable presentation. And before that, I would like to introduce Dr. Rana. Dr. Biswarup Rana received his PhD from Indian Institute of Engineering, Science and Technology, Shibpur, India in 2017. He was a postdoctoral researcher at Seoul National University of Science and Technology, South Korea. Currently, he is with Konju National University, South Korea. His research interests include the analysis and design of microstrip antennas, substrate indicated waveguide antennas, phased array antennas, dielectric resonator antennas, implantable antennas, transmit arrays, reconfigurable intelligent surfaces, and meta-surface design using AI or ML. Dr. Rana is a reviewer for various Nature and IEEE journals. He will be joining Konju National University as a research professor starting from March 1, 2025. He has authored over 80 journals and conference papers and is the inventor of 3 patents. So now I will request Dr. Rana to proceed with your presentation. Thank you.
Okay, thank you. Can you hear me?
Yeah, you are clearly audible.
Okay, a very good afternoon to all of you. I am Biswarup Rana. Actually, I am from West Bengal, India. Now I am living in South Korea, maybe more than 6 years. So today I am going to present one of the very important area, that is the dielectric resonator antenna for RF energy harvesting. Now, for energy harvesting, the main problem is the efficiency. Actually, if you see the 5G communication or 6G communication, for 6G communication, there is no such maturity of the energy harvesting devices. So there are a lot of technologies out there, and every technology is going to mature in future. Now, dielectric resonator antenna and substrate integrated waveguide-based antenna is going to be a very important area for this type of RF energy harvesting, because the efficiency of RF energy harvesting is very important. So when there's efficiency, then normal patch antenna has inherent loss. The loss is like conductor loss, but the dielectric resonator antenna and substrate integrated waveguide antenna, for dielectric resonator antenna, this type of antenna, they don't have any type of conductor loss, only dielectric losses are there. So this is very efficient antenna for energy harvesting. Also, another technology, that is substrate integrated waveguide based antenna. The substrate integrated waveguide based antenna is very important, because if you see the metallic waveguide, in metallic waveguide, the losses are almost very negligible. When the wave is propagating, the propagating, then inside the waveguide, then loss are extremely low. So this type of SIW technology can be very useful for RF energy harvesting devices. But still, people are not. There's some paper out there in literature where they are discussing that how we can use direct resonant antenna for energy harvesting. But I think that a direct resonant antenna and substrate integrated waveguide antenna will be very good for energy harvesting devices. So today I will be discussing, first I will discuss the substrate integrated waveguide based antenna. After that I will be discussing the dielectric resonator based antenna. And these two type of antenna is going to be very important for future. But most of the people are doing research on patch antenna. But the patch antenna has one problem. That the problem is that it has narrow bandwidth. Let's say for normal operating frequency, the bandwidth is almost 4%.
And
But for this dielectric resonator, for the dielectric resonator based antenna, hello.
Dr. Rana, I think that is there any issue in your internet connection? Your voice is breaking from my side.
Breaking?
Actually, from my side, I can see that your voice is breaking.
Now can you hear me?
Yeah, you are
Yeah,
audible, sir. Please proceed.
yeah. Please go ahead.
Okay. Actually, maybe for long distance from India to South Korea, so maybe that's why. Okay, no problem. So outline today I'm going to discuss first is the introduction and literature review of substrate integrated waveguide. Next, I will going to discuss half mode substrate integrated waveguide feed complex slot antenna. Then I'm going to discuss each plane horn antenna using corrugated substrate integrated waveguide. The half mode, after that I'm going to discuss the cavity back antenna using corrugated substrate integrated waveguide. The next is the dielectric resonator antenna. Next I'm going to discuss dielectric resonator antenna based array, that is the microstrip line feed. And in normal communication, let's say if we have one polarization, then normal for 5G communication or any other communication, most of the antennas are dual polarized antenna. So dual polarized dielectric resonator based antenna is going to have a very profound impact for antenna designer. So dual polarized, why we need dual polarized? Because for one polarization we can send one signal and another polarization we can send another signal. So the channel capacity will be doubled with the dual polarization dielectric resonator based antenna. So this is very important. And next is the dual polarized dielectric resonator antenna using frequency selective surface. I'm going to discuss this area. Next, I'm going to discuss microstrip line feed wideband circularly polarized dielectric resonator antenna array. Next, I'm going to discuss non-resonant microstrip patch feed dielectric resonator antenna array. Because non-resonant microstrip patch feed, we want to excite the hybrid electromagnetic 1 to delta mode. The gain is very important for any antenna, because if the gain is very high, that means more amount of power we can transfer. So if we can transfer more amount of power, that means more data can be transferred. So gain, and another thing is that polarization. These two parameters are very important for any antenna for practical application. After that, I am going to discuss circularly polarized cylindrical dielectric resonator antenna with helical exciter. And after that, I'm going to discuss circularly polarized rectangular dielectric resonator antenna. Then we can integrate the SAW and dielectric resonator antenna to get substrate integrated feed cylindrical dielectric resonator antenna. Next, I will discuss some energy harvesting dielectric resonator antenna, because in literature, the dielectric resonator antenna for energy harvesting are very limited. So I can show the one structure and one dielectric resonator antenna, and I can show that how this dielectric resonator antenna can be integrated for energy harvesting devices, and I will discuss on paper. Next, I will conclusion and references. So this one is the substrate integrated waveguide. So when the frequency is very low, then normally we can use normal microstrip patch antenna or coplanar planar waveguide. But when the frequency is very high, let's say the frequency is 30 GHz or 40 GHz or above, then conductor loss for this type of microstrip antenna are very high. Then we need to think about different type of antenna technology or different type of technology where the loss is minimum. And the main for this energy harvesting device, as I already mentioned, that efficiency is very important. Because of efficiency, still the energy harvesting devices are not so mature. In commercial it is not so mature. So the efficiency is very important for this type of energy harvesting devices. And so we need to, at high frequency, the transmission loss and radiation loss prevent the use of microstrip and coplanar waveguide, and other technologies solution have to be have to be identified. So a promising candidate is the substrate integrated waveguide. So substrate integrated waveguide is just like this one is the top metal and this one is the ground metal, and these are the vias, and the vias are consist of metal, and uh, we need to place this via a certain particular distance, otherwise there will be energy will be leaked from this structure. So within this structure, the TE mode can propagate very well. So let's say TE10 mode or TE20 mode and other mode, it can propagate very well, but the TM mode cannot propagate. But for any communication, the TE mode is enough for normal power transfer. And another important thing is that this SRW structure can preserve all the advantages of conventional metallic waveguide, namely high quality factor, high power handling capability with self-consistent electrical shielding. So this one is the introduction of SRW structure. Now the SRW structure can support TE mode, but it cannot support TM mode, because this is the current distribution for TE mode. For TE mode, you can see the current are parallel to the slot. This is one slot, this is another slot, another slot, another slot. So this is the SRW structure. But for the TM mode, the current will be this one slot and current will be this direction. So this another slot and current will be here. So the current and the slot are at 90 degree. So there will be significant amount of losses will be there. So this structure cannot support TM mode. This structure can support only TE mode. So this is the current distribution for TE10 mode. Also, it can support TE20 mode and other type of modes. Now, as I already mentioned, that SRW structure exhibit the properties similar to the metallic waveguide, and the losses are very minimum. And because of this symmetricity between the metallic waveguide, and there are some formula in the literature. So this one is the first formula, and here W is the width of this one, and D here D is the diameter of the via, and S is the distance between these two via, and W effective is the width of the effective of the conventional waveguide. So this is the conventional waveguide width, and this is the width for this structure. So this one is the one formula, but this formula is not so accurate one. So another formula was proposed. This one is more accurate compared to this one, and here the same thing is that the W effective is the width of the conventional waveguide, and W is the width of this SRW structure, and D is this thing. And this formula was also proposed. Another formula, this formula is very good one. So if you want to calculate what is the effective width of this one with effective width, or compared to with the effective width of waveguide, rectangular normal waveguide, rectangular waveguide. So this formula is very good one. So the SRW structure exhibit proportion characteristics similar to those of rectangular and metallic waveguide, provided that the metallic wave vias are closely spaced and radiation leakage can be neglected. And as I already mentioned, that SRW particularly coincide of the subset of guided mode of rectangular waveguide, namely TEN0 mode. So N can be here 1, 2, 3, 4, etc. any other mode. So it can support, but it will not support the TM mode. So owing to the similarity between this one and this one, these are the formula proposed in the literature. This is the operating principle of the SRW structure. Now, loss, mechanism, bandwidth, and of the SRW structure. So the key issue of the SRW structure as the loss minimization, which is particularly important for millimeter wave frequency. So to overcome these losses, different type of technique used. So different type of losses are there in SRW structure. First is the conductor loss. So this conductor loss is basically the finite conductivity of the conductor, and second type of loss is the dielectric loss. This loss due to the lossy nature of the dielectric material, and third loss is the radiation loss. This loss due to the leakage from the SRW structure. So uh, in literature, the authors propose the substrate integrated folded waveguide can be used for, I mean, the size reduction. So using this technique, the size can be reduced half. Now another technique, this is known as half mode substrate integrated waveguide. So in this technique, the mode will be same, but we can cut the waveguide into two pieces. So we can take one pieces. This one pieces is known as half mode substrate integrated waveguide, and this waveguide structure is very important for any antenna design or any transmission line or any other power divider design. So the SW structure is basically for the circuit people who are working with the circuit, like power divider, coupler, or any other circuit. This SW structure is very important. A lot of people are also trying to design SW structure antenna, but the problem is that this SW structure antenna has very less bandwidth. Bandwidth is very narrow. But for normal communication, we at least for industrial application, we need at least 200 megahertz bandwidth. But sometimes the bandwidth is less than 200 megahertz. So we sometimes it is, the antenna is very good one, but nowadays people are proposing a lot of type of different type of approach, so that it can be used in normal, in industry. And another type of technique is that folded half mode substrate integrated waveguide. Using this technique, we can fold the SRW structure with half mode, and this structure can reduce the size. And this another structure is known the substrate integrated slab waveguide. It improves the bandwidth performance, and also in literature there are other technique by which the bandwidth can be enhanced, like different type of slot, zigzag slot or meandering slot type of thing. So using this type of technique, it is possible to enhance the bandwidth of the SW antennas. This is the first proposed SW structure in the literature. In 2004, Li Yang et proposed the first SW structure, and this one is the SW vias are there. This is like waveguide. So this is one waveguide, another waveguide, another waveguide, another waveguide. So four waveguide embedded inside, embedded in PCB structure. So this PCB waveguide, you can say this is one sort of PCB waveguide, and we have 1, 2, 3, 4 slot here, and this one 4 slot, total 16 slots. So total number of slot are there here, 16 slot. And these are the SW structure, and this one is the power divider. So the power is going here. Maybe this is the 50 ohm line. After that, lambda by 4 transformer. After that, they have used this type of power divider, and this antenna is resonating at around, let's say, around 10 gigahertz. It is resonating, and this one is the first SW structure proposed in the literature, and this is the E-plane radiation pattern at 10 gigahertz, and calculated directivity is 17.4, and measure gain was 15.7 dBi, and transmission loss was 0.1. And this one is the E-plane radiation pattern at 10 gigahertz, and the feed loss was 0.7, and conductor loss was 0.4, and unaccounted loss or different type of loss was there, that was 0.5. Now in SRW structure, the distance between two via should be very small, so that there should not be any amount of power should not be leaked from here. But if the via is very large one, so some power will leak from here. So this type of antenna are known as leaky wave antenna. Leaky wave antenna was proposed 2005. And another leaky wave proposed, that is they use the TE20 mode for service structure. And these two paper, this is the cavity back SRW structure. So cavity backs, let's say we have some resonator. Let's forget about this type of SRW structure. We have some normal waveguide resonator. In waveguide resonator, there's a different type of resonance is there. So in that resonator, if we put one slot, and from the slot there will be radiation. So it can be treated as an antenna if we put on slot. So similar type of thing is there. Here we have 50 ohm line, and this one is the resonator. So all waves, the field are resonating here. And after that, if I do on some sort of slot here, then from this slot we can have some radiation. So this type of antenna are known as cavity back SRW antenna. And this one is the fabricated one, and the mode here is for this type of antenna is TE120 mode. So why one? Because in this direction we have only half wavelength variation. If they say half wavelength variation, then this index is 1. Now in this direction we have two length variation. This is 1 and the 2. So this one is the 2, and Z, along the Z direction there is no variation. So that's why it is 0. And the distance between if this is the diameter of the via, and if dp is the diameter, dp is the distance between two via, then d by dp greater than equal to 0.5 to have this type of structure. Also d by lambda 0 less than equal to 0.1 for proper operating of this type of antenna. And this is the return, this is the S1 parameter. An S1 parameter, you can see from this figure that this antenna is resonating around 10 gigahertz, but the bandwidth is very narrow. Still it is more than 200, so it can be used in practical scenario. And maybe 1.7% bandwidth and 5.4 dBi gain and 16.1 dB front to back ratio and minus 16 dB maximum cross pole radiation. And this is the radiation pattern for the antenna at 10 gigahertz. This is another cavity back slot antenna. Same type of concept, that we have one cavity, and cavity we have all the wave are resonating there. And here if we put some slot, then from slot there will be radiation. So in the previous design, the slot was linear, but here they have put this type of zigzag slot. And because of this slot, it can have some miniaturized, the antenna will be miniaturized. The miniaturized antenna can be designed with this type of zigzags, and it is operating around 3.02. And the mode is here TE10 mode, and the bandwidth is 1.32, 8.5 dBi gain, and front to back ratio is 21 dB. And this is the simulated and measured E-plane radiation pattern. This is the E-plane measured radiation pattern, and this is the E-plane simulated radiation pattern, and simulated and measured H-plane radiation pattern, and distribution of current on this cavity bottom phase. This is the current distribution. And concept of half mode. So this structure are basically the full mode. Now in normal SRW we have one structure. This is one via this side and another via this side. Now this is the concept of half mode waveguide. In half mode waveguide we have only via only one side, and this is the electric field distribution of the half mode SRW. And the opposite side of the half mode SRW is the open circuited, but still there is no leakage from this one because this one is acting as a magnetic world, so there is no type of radiation, no type of leakage from here. So the H, I mean the half mode SAW support, I mean M minus point, I mean 0.50. So M can be 1, so the mode will be TE 0.51 mode. If M is 2, so 1.5 mode. So this type of mode can propagate through this SRLU structure. And this one is the electric field distribution. And this is almost similar to electric distribution of the rectangular waveguide with a dielectric media. If we have on a rectangular waveguide with dielectric media, the field distributions is exactly similar to that one. Now this is the transmission characteristics of the substrate integrated waveguide, and we have here this is the SRW structure. We can put one port 1 here, and this is the port 2, and after that we can measure what is the S1 parameter, and we can check what is the S21 parameter. And for this type of design we took Arlon substrate. The permittivity was 3.2 and height 0.7 millimeter and loss tangent 0.002, and distance between the two via was 1.5 millimeter, and cutoff frequency was 11.8 gigahertz. And that was the SRW structure. Now if we close the SRW structure, so it will act as a resonator. Now if we put on slot here, then from the slot we have one radiation. So this is one structure here. This is the port 1. So from port 1 the power is going here, and the all power is confined here like normal resonator. Now if I introduced, if I introduce one in a slot here, then the from slot there will be radiation. So here introduce one slot, and from here the slot is radius, and from this structure you can see that SLW structure resonating around 17.8 gigahertz, and E plane and H plane gain are 5.5 dBi, and cross propagation level is less than minus 18 dBi. And this is the half mode SRW compact slot antenna, and this one is the fabricated. This is the top view, and this is the bottom view. And we can that was the full mode. Now if we cut this full mode into two pieces, then we have one half mode. And this half mode, as I told, that if there is a magnetic wall there, then there will be no leakage from here. So we have here one antenna. If we introduce some resonator, I mean slot here, so from slot there will be radiation. So this is the top view of the structure, this is the bottom view of the structure, and this is the simulated and measured S1 parameter, and this is the radiation pattern, E plane and H plane radiation pattern. Now instead of one slot we can introduce three slot. So like normal waveguide there's a one slot. So and if we put number of slot, then there will be constructive interference, and if there's a constructive interference, then the gain will enhance. So similarly, similar concept is here. So this one is the resonator, and in this resonator we are giving one slot. So from one slot there will be radiation, so another slot there will be radiation, another slot. So one particular phase point, like I mean for one particular point, the radiation will add. This is constructive interference and will get enhanced gain. So if you want to design the antenna array, this type of concept is very important. This is the top view and this is the bottom view, and this is the S1 parameter for this type of half mode SW, and this is the radiation pattern for half mode array, and this is the H plane radiation pattern. Now another concept is that corrugated substrate integrated waveguide. So in conventional SLW structure we have via here. So this type of via is there, but if we want to fabricate the via, we need some drilling machine or any other technique, so it is very difficult. So instead of this thing, we can introduce here the quarter wavelength transformer. If we use quarter wavelength microstrip open stub, then it can act as a artificially electric side wall, so the wave will propagate through this waveguide structure, and it will be like the waveguide structure, but this structure is also very good one. But in literature nowadays in Chinese, I saw in 2020, maybe 2023 or 20, the Chinese authors, they have proposed this type of corrugated substantive waveguide based array, and after that they fabricated a lot of antenna array with this technique. In literature there is a very limited paper. So corrugated SRW is a new type of transmission line where we have, this is the port 1 and this is the port 2, and this one is the uh, quarter wavelength microstrip open circuit stub here, and this one is also quarter wavelength open circuit stub. This corrugated SRW structure preserve most of the advantages of conventional metallic waveguide, namely high quality factor, high power handling capability, compact everything. But we have the advantage of conventional metal waveguide or SRW structure. It can preserve all those advantages. And uh, also another important thing is that the fabrication is very easy for this type of structure. And corrugated SRW structures support TE mode, 10 mode, T20 mode, or any T or TN0 mode. Also, it can support transverse ETEM mode. Also, this corrugated waveguide composed of one thing is that host waveguide. So this one is the host waveguide. In host waveguide, we have one port one is there, another port 2 is there, and microstrip stub are connected each side of the host waveguide. Now, here we can fabricate a horn antenna based of this technology. So this is known as CSW based H-plane horn antenna. In this design, the dielectric constant was 4.4 and height was 1.58, loss tangent was 0.02, and this dispersion characteristics of this CSI was similar to the conventional SRW or similar to the metallic waveguide, and this structure propagate T10 mode, and the cutoff frequency was 6.8. But the problem here is that this is not as efficient as SRW structure, because SRW structure has almost the amount of loss is very low there, but here the amount of loss is little bit higher compared to SRW structure, but still is very new type of concept. So using this with this concept, we can propose different type of antenna, and the stub width was 0.3 millimeter and distance between the stub was 1 millimeter, and we need to the stub width and the distance between the stubs should have particular dimensions to minimize the zero dimensionally lump shunt admittance can be neglected. So using we need to use this type of dimension to reduce the zero dimensional lump shunt admittance. And because of this SLW, we have some fringing field from here. So the waveguide width, if we say the A, but the actual waveguide will not be A, because this is similar to the microstrip line. If microstrip line, if there's some line is there, the actual width is not W, but some fringing field is there. Because of the fringing field, we have the effective W. Similar thing is there. So here, let's say we have width here, because of fringing because of host waveguide, the width will not be A, but it will have equivalent width A plus 2W. And delta W, in this structure we have calculated that it is 0.2 millimeter, and equivalent width of the host waveguide was calculated as 10.4 millimeter. And the cutoff frequency of such waveguide can be calculated using this formula. And here the cutoff frequency is almost 6.8 here. Now we can use one formula here. Let's say this is one formula, and here R of t, we can put R of t, let's say 19.6 millimeter. After that we can figure out, we can put W3 is 29 millimeter, and we can put R of t 19.6, and we can calculate what is the what is the where we need to set W29, and we can need to calculate R of t, so 19.6. And also we can calculate theta here, and this is the 50 ohm line, and here is the flare section, and from here we have this type of antenna, and the antenna was fabricated, and this is the S1 parameter of this proposed antenna, and this is the simulated and measured radiation pattern. And for this type of antenna we got the bandwidth of 16.5, covering frequency from 8.3 GHz to 9.9 GHz. And these are the radiation pattern for E-plane radiation pattern, and this is the H-plane radiation pattern, and this is another frequency E-plane radiation pattern, this is H-plane radiation pattern. And this one is the cavity design of corrugated cavity based slot antenna. So previously in literature, the lot of authors propose that cavity back slot, SRW based cavity antenna, but here we can use this type of technique, the quarter Williams transformer, and after that we can design one cavity here, and we can introduce slot here, so that we can get cavity back slot antenna. And for this type of design we took Arlon AD27 substrate with height 0.79 millimeter, relative permittivity was 2.7, and loss tangent was 0.02, and antenna size was 60 into 60 into 0.79 millimeter cube, and resonant frequency of this antenna was 5.07, and bandwidth was 3%. And this is the E-plane and H-plane radiation pattern of this proposed antenna. Now this thing, now I'm going to discuss dielectric resonator antenna. Actually, initially before maybe 20 years or 30 years ago, dielectric resonator was used as a resonator circuit. So because a resonator, why? Because it has high Q factor. If this is high Q factor, it can store a lot of energy. So if it can store a lot of energy, that's mean we can use as a resonator circuit. So but in 1980, these authors they have checked that if we reduce the permittivity little bit lower, let's say the permittivity of the dielectric resonator antenna 100 or 200, then it cannot radiate. But if the permittivity of dielectric resonator antenna is 10 or 20, then this author check that it is radiating perfectly well. Another advantage of this dielectric resonator antenna is that it has no conductor, so there is no conductor loss of this type of antenna. And after that, the authors study different type of shape, like triangular shape, spherical shape, cylindrical shape, different type of structure they have studied, and they publish a lot of paper. So this is the dielectric, these are the dielectric resonator antenna and the feeding structure. So advantage of dielectric resonator antenna is that design and shape flexibility. So dielectric resonator antenna can have different type of shape, like rectangular shape, circular shape, elliptical shape, or any other shape. and wide impedance bandwidth. If we say that this is one example, for this example, the microstrip patch antenna is resonating at, let's say, maybe 35 gigahertz. So at 35 gigahertz, the bandwidth of this microstrip patch antenna is 2.6 gigahertz. But the dielectric resonator, the bandwidth of the dielectric resonator antenna is almost 15.6%. So we are getting very higher bandwidth of this type of for this type of, I mean, for you can see from this picture. And another important thing is that easy of integration with other antenna. So dielectric resonator antenna can be integrated easily with other type of antenna. So this is another advantage is there. And main advantage is there for normal metallic wave, but if frequency is 30 gigahertz, if you want to design one antenna 30 gigahertz, maybe 30 gigahertz it will work, no problem. If you want to design 40 gigahertz or 50 gigahertz, then microstrip antenna will have very strong, I mean, will have very large losses. So if you want to design very high frequency antenna, then this microstrip antenna will not be good one. So we need to we can use this dielectric resonator antenna or a cerebral structure antenna or any other type of antenna. So this dielectric resonator antenna is very good for higher frequency application, and this dielectric resonator antenna also can tolerate high temperature, and we can excite the dielectric resonator antenna by different techniques like normal microstrip line feed or coaxial feed or any other feed we can use to excite this type of dielectric resonator antennas. Now feeding structure, suppose in a volume V, we have two current source, let's say J1 and J2, and these two current source is giving rise to two electric field. One is the E1 and E2. So inside this volume, we have another magnetic current, that is M1 and M2, and these two magnetic current are giving the field that is H2 and H1 and H2. So this Lawrence first observed this thing, and he said that the surface integral of E1, if this is the electric field responsible for this current, and this is a magnetic field, M2 H2 is the magnetic field responsible for M1 current, then E1 cross H2 minus E2 cross H1 dot ds is equivalent to this one. So this is E2 dot J1 minus E1 dot J2 minus H2 dot M1 minus H1 M dot M2 dV. Now if we can arrange this equation and we can get this thing, that is E1 dot J2 minus H1 dot M2 whole dV volume integration is equal to E2 dot J1 minus H2 dot M1 dV. So from this equation, this electric field and this is the electric field and electric car, this is the electric field and this one is the electric field. So we can equate this one, E1 J2 is equivalent to E2 dot J1 and H1 dot M2 equivalent to H2 dot M1. So we can say that the electric field, this E1 along the source J2 is equivalent to electric field E2 along the source J1. So if we have one dielectric resonator antenna and if we have some electric field, or I mean if we have some electric current, or if we have some magnetic current, then this electric current and this magnetic current can give rise to electric field or magnetic field. So this is the electric field part and this is the magnetic field part. So any dielectric resonator antenna, we have, suppose we have some electric field, I mean electric current is there. So the dielectric resonator antenna here, it will couple the electric field because of this electric current. So the coupling, how much amount of coupling will be there? The coupling amount, the K, is proportional to E2 J1, I mean J1 dV volume integration, and for the magnetic source, the this K will be H2 dot M1 dV and volume integration. So I can show an example, so how it can work. So let's say this is the dielectric unitary antenna. We have one dielectric unitary antenna here, and this one is the slot, and this one is the microstrip line. So this microstrip line is there, and this slot is there. So this slot, this microstrip line, from this microstrip line, the power will couple here, and some power will go couple from here to here. Because of power coupling, and this is a slot, so it will introduce magnetic current. We can say this is the magnetic current. If there's a magnetic current, then magnetic field will be introduced here, this dielectric unitary antenna. So this is like this type of thing. So we can say that this is the short magnetic dipole current. Magnetic current is there, this magnetic, because of this theorem. So because of this theorem, so if there's a magnetic current, then magnetic field will be introduced here. So this magnetic field will be introduced here, and because of this magnetic field, it will behave as the magnetic short dipole. And if this is a magnetic short dipole, it will radiate as a short magnetic dipole. So the radiation pattern will be like the short magnetic dipole for this type of configuration. And this is the top view of the feeding structure, and this is the magnetic, so for this structure, this is the short magnetic dipole, and this is the magnetic field, and this is the top view of this type of structure. So for this type of configuration, the length, this length, first we need to calculate the effective epsilon r. This is effective epsilon r e is equal to epsilon r. So what is the permittivity here, and epsilon s, what is the permittivity, this substrate, divided by 2. And if we can get epsilon e, and we can put here, we can calculate what is the length here, and length will be 0.4 lambda 0 by root over epsilon e, and this width will be 0.2 lambda s. So we can calculate what should be the length and what should be the ws for this type of feeding structure. Now similar concept, if we have some probe is there, this probe can be thought as say that it is some, it is radiate, this is the current. We can say that this is the probe, so it is, here the electric current is flowing. So if this electric current is flowing, also we have a magnetic field here is there. So if this is electric current is there, then the electric field will be introduced. Also we can think about different configuration, that there's a magnetic field is there. If there's a magnetic field and this magnetic, if the magnetic current is there, then magnetic field will be introduced here. So same type of thing, that we can think about this one as a magnetic field is introduced from this coaxial probe from here to this dielectric unit antenna, and it will be a short magnetic dipole. So the radiation pattern will be like short type of magnetic dipole, and this is the magnetic field here. And for this type of dielectric unitary antenna, this is the, if this is the feeding structure and this is the slot, so because of the slot we will get the here magnetic current, and because of magnetic current the magnetic field will be introduced here. And this is the microstrip line. So microstrip line has electric field like this type of thing, but the magnetic line of force will be like this type of thing. If the magnetic line of force is this one, and magnetic field will be introduced, and it will radiate as a short magnetic dipole. The same concept here is there. So here we can think that some magnetic field is coupling from this probe to here, and it is radiating. So radiation pattern of the dielectric unit antenna, the fundamental mode of the dielectric unit antenna are the magnetic or electric dipole. So it will radiate like magnetic dipole or electric dipole, and the radiation pattern can be expanded using a multiple expansion technique. And this multiple expansion technique, any arbitrary radiation pattern can be decomposed into a sum of dipole and quadrupole or higher order multiple terms. And also we can get circular polarization. If we want one field and another field 90 degree, then we can get also circular polarization. So if we can introduce one mode here. Let's say we are getting one mode, that is the HE11 delta mode, and another mode we are getting HE11 delta mode. But these two modes are excited at 90 degrees. Then we can get the circular polarization for this, for direct unit antenna. And different modes are there in direct unit antenna. This first mode is the HEM11 delta mode. So the first term one, this is the, this is the azimuthal variation. So in azimuthal variation, we have one variation, and this is the radial variation. What is this one variation? And delta means along the z direction we have some variation, but this variation is very negligible. The variation not half wavelength or not lambda by 4 or not lambda by 8, but very small variation. If there's very small variation, then we can put the lambda. So the nomenclature of this first is the uh, first is the azimuthal variation, next is the axial variation, and next one is the variation along the z direction. Now this is the electric field distribution for the TM01 delta mode, and this is the hybrid electromagnetic 1-2 delta mode. Actually, if exciting this type of mode is extremely difficult, because if we want to excite HEM1 to delta mode, then this, you can see, this is the top view and this is the side view. You can see this is the electric field distribution. But if we put one in any type of conductor plane, then this field will not be like this one. So the field will go this direction and this, and there will be no field here. So exciting HEM1 to delta mode is not easy one. So because to excite this type of mode, you can use different type of non-resonating microstrip patch structure or this type of structure to excite this type of mode. The advantage of this mode is that we can get high gain with this mode. And this one is the dielectric unit antenna, and this is the width, and this is the microstrip line. The same concept is there. Microstrip line is propagating electric field, and also we have the magnetic line of force is there. So from magnetic line of force, the energy is coupled from here to here, and from here the dielectric unit antenna is rotating. So the different electric field component and different the magnetic component inside this dielectric unit antenna, like Ez along the z direction of the electric field is almost 0, and this is Ex Uy component, and this one is the Hx Hy Az component. And this dielectric unit antenna satisfy this equation, and this one is the our work. So this is simulated single element dielectric unit antenna. This is the deflection coefficient of a single element antenna or Smith chart. A simulated S11 parameter for different length of this dielectric unit antenna. This is simulated S11 of the single element dielectric unit antenna for different value of the height. And this is the resonant input resistance of the dielectric resonant antenna for different L by A. The side view, side view of the electric field, this is electric field, and this is the radiation pattern. And you can see from here that if the microstrip line width is very small one, width is not so large, then the amount of coupling from the microstrip line to here is very negligible. But if the microstrip line width is very large one, the amount of coupling is very high one. So if you want to have very good matching between the microstrip line and the dielectric unit antenna, then we need to use this type of large microstrip line. And this one is the fabricated structure. This is the top view and the proposed top view of the, and this is the side view, and this is the simulated and measure S11 parameter. And this one is the radiation pattern. This is the E plane radiation pattern, and this is the H plane radiation pattern. And simulated efficiency was almost 98.5. And dual polarized dielectric unit antenna using microstrip line feed. So the same technique we are using here, that we microstrip, and we are using two port. One port here. So from one port we are exciting one mode for this type of directly generated antenna. We are exciting here TE11 mode for this from this side. So this is TE1 mode for one plane, and this is the TE11 mode from another side. So we are getting here dual polarized directly generated antenna, and the antenna is generating around 6.6 gigahertz. And this is the S1 parameter, and this is the E plane and H plane radiation pattern for this type of dual polarized antenna. Now we can, for normal communication, if we want to design one array, then if we want to design one array, then there will be constructive interference. If there is constructive interference, then gain will be enhanced. If there's a gain is very high, I mean the gain is very high, then more number of data we can transfer from one point to another point. So that's why we design here dual polarized antenna using microstrip line feed. And here we design one line. This is the 50 ohm line, this is on the 100 ohm line. After that we put here quarter wave transformer. After that, this one is the 50 ohm line, 100 ohm line, again quarter transformer, 50 ohm. So this one is the normal power divider, and here we have again same power divider, but this is the from this side we are getting the electric field from this side, and this is the electric field from this side. So this is the dual polarized antenna, and this is the S1 parameter of this type of antenna. This is the E plane and H plane radiation pattern of this antenna. Now we can also think how we can get the circular polarization. For circular polarization, we need two modes. One mode is here, one direction, another mode from another direction, but the mode should have phase difference of 90 degree. So here we are introducing one, here we have one microstrip line, here we have quarter wave transformer. After that we have again one line, 50 ohm line. So after that we are introducing here quarter wave, maybe 90 degree phase by this line. So if this is 90 degree and this is one mode there and this is another mode there,
Dr.
and
Rana, Dr. Rana, just I
yes,
have one query. Just here you are showing that the microstrip line fed wideband circular polarized DR array, but I can see that only one DR is there.
which one? This one?
Oh, okay. I think that in this slide, in that slide, you can see only one DR is there. In the next slide, in the
Here?
next slide.
No.
Yeah.
Oh, we have array. Oh, I'm discussing the array. So this is the
Okay.
only one. So first we need to design the single element array. After that, this is the E plane H plane radiation pattern. After that, we have designed the here. So this is the initial part of our work. So this is the initial part. This is the single element. After that, this one is the array. So here we are designing 1, 2, 3, 4, and this is the I mean, this one is the one mode here, this is another mode, and the phase difference is 90 degree we are getting. So if the phase difference is 90 degree, means we are getting circular polarization. So this is the S1 parameter, and this is the axial ratio of a circularly polarized, and this is the E plane and H plane radiation pattern. And this one is the gain for the circular polarized antenna. Now also we can design dual polarized antenna using frequency selective surface. So the one advantage of frequency selective surface is that we can get the higher gain with this type of frequency selective surface. So this is the normal dual polarized direct unit antenna. So we have one direct unit antenna, we have port 1, this is port 2, and this is the fabricated prototype. After that, this is the S1 parameter, and this one is the E plane and H plane radiation pattern. And we have designed this type of frequency selective surface, and this frequency selective surface, we have this one is the patch, and this is this type of structure, and this is the dielectric substrate. This is the dielectric substrate. This one is also dielectric substrate. So equivalent circuit will be like this one. So for this upper patch, we have C1 here, and for the lower patch, we have C3 here. And for this structure, I mean, for this structure, for for this structure and this structure, we can think about the transmission line. So for this two structure, we are getting one C, and for L1 here, and this is for another C, and this is another 4, and this L is because of this one. So for this one, we are getting L1. So this here we are getting one T structure. From the T we can transfer to T network to pi network, and we can calculate what is the value of L1 and what is the value of L3, what is the value of LM and C1 and other component, and we can get one circuit model, and we compare the circuit structure with the simulation result. And this is the S1 parameter, and this is the S2 parameter, and this is the E-plane radiation pattern. This is the H-plane radiation pattern, and this is the E-plane radiation pattern from port 2, and this is the H-plane radiation pattern for port 2. Now we can also design dielectric resonator antenna with non-resonating microstrip line fit. The basic principle of non-resonating microstrip line fit is that if we want to have higher gain, then we need to excite higher mode. That is, the mode is HEM onto delta mode. For this mode, if we can excite this HEM onto delta mode, then the gain will be very high one. So the gain will be very high one. Now if we can design 2x2 array with this HEM onto delta mode, then gain will be more higher. So this will be very suitable for normal and industry application. So here the problem is that if we want to excite HE1 to delta mode, we need to have one non-resonant patch here. Because of non-resonant patch, these two things, for this type of mode, I can show you. For this type of mode, so because of this non-resonant, this electric field the electric field will be preserved. Electric field will be like this one. If there is no non-resonating mode, then electric field will not be like this one, and you cannot excite the HEM onto delta mode here. And after that, the distance between the two dielectric resonator antenna is basically lambda by 2. If for lambda by 2, and normally for if any array design, the distance between two radiators normally are lambda by 2. So this is the top view and the bottom view, and this one is this parameter, and this is the S1 parameter, and E-plane radiation pattern, H-plane radiation pattern. Now also we can design a circularly polarized dielectric resonator antenna with helical exciter. So like helical antenna, like if I have some helical antenna, if we put dielectric resonator antenna there, then it will like helical loaded, dielectric resonator loaded helical antenna. So this type of antenna also very important for different type of satellite communication or this type of thing. In satellite, you can see a lot of helical antenna there. So also we are trying to design the helical exciter here, high gain circular polarized antenna, this type of helical antenna, and the turn was 6 turn. And this is the first is the power divider. We have the 50 ohm line. This is the 100 ohm line. After that, we have the quarter ohm transformer, and this is the 100 ohm line. This is the 50 ohm line, and we are giving port feed here. So the power is going from here. So everything is matched here. The power is going here. And the problem here is that and this is the helical exciter. From helical exciter, the antenna will detect. Another thing is that for this type of helical exciter, we can get the circular polarization. So Circular polarization is the main function of this type of helical exciter. And this is the S1 parameter and radiation pattern, E plane, H plane. And this is the axial ratio of the helical exciter. Now also we checked circularly polarized rectangular shape. That was the that was the I mean rectangle. I mean that was the circular. I mean cylindrical shape. This is the rectangular shape direct unit antenna, and this direct unit antenna offered 12.9 dBi gain at operating frequency. Prototype also fabricated. So this type of helical exciter and the same configuration, instead of that thing, we here we have used here one, I mean rectangular shape dielectric, and after that we have used some helical exciter. From helical exciter we are getting circularly polarized wave, and this is the S1 parameter, and this is the E plane radiation pattern, this is H plane radiation pattern, and this is the simulated peak gain for different inter-element space and simulated and measured axial ratio of the proposed antenna. Now this one is the very important thing, that we can integrate both SRW and as well as a dielectric unitary antenna to get SRW feed dielectric unitary antenna array. So the power, so normal power, instead of normal power divider, we can use the SRW structure, because SRW structure preserve all the advantages of the conventional waveguide. So we can use the SRW structure, and we can have some slot here, and we can put a lot of direct unit antenna, and we can get the substrate integrated waveguide feed cylindrical and direct unit antenna array. This is the E plane radiation pattern, and return, I mean this is the S1 parameter, and this is the VSW1 E plane radiation pattern without DRA, E plane radiation pattern with DRA, and 3D radiation pattern. And this is the same thing that here, instead of this is the different frequency. Maybe this frequency was 13.35.8 gigahertz, and this was designed at maybe 14.205 gigahertz. But the problem is that the bandwidth is very narrow here. And this is the S1 parameter, radiation pattern with DRA and without DRA. And this is the 3D radiation pattern without DRA, and this is the 3D radiation pattern with DRA. And this proposed antenna resonate at 14.1 to 14.7 gigahertz with 5.1% bandwidth. And this type of antenna has very low cross polarization. Maximum gain was 7.14 dBi for both E plane and H plane. Now energy harvesting of the direct unit antenna. So I discussed the SLV structure and direct unit antenna. So this SLV structure and direct unit antenna are very promising candidate for the energy harvesting. So for the energy harvesting, we have the transmitting antenna. So the transmitting antenna, we can put one a direct unit antenna here or SLV structure here, and for the we need some matching network and rectifier and the power management and application. So this is the basic block diagram of the energy harvesting. So I think, because for energy harvesting there's no such, I mean the paper are very limited, not such paper. Most of the paper are like they are using patch antenna, but because of that patch antenna the efficiency are very low and they are not getting very good result, and it cannot be used as a real-time application. But this dielectric unit antenna and substrate integrated waveguide based antenna will be very promising candidate. But there's not such a amount of paper in the literature, very limited paper are there.
Dr.
Here,
Rana,
yes,
Dr. Rana, I want to comment one thing, that if we use SIW, that is substrate integrated waveguide in energy harvesting applications, Then
Hmm.
actually, energy harvesting applications, the antennas which are used in these purposes are mostly placed in wireless sensor nodes. So in a
Yes.
remotely located wireless sensor nodes, can we implement such kind of SIW type of antennas which are very bulk carrying structure? This is my
Yes, we can use. Yes, we can use cerebral structure because of this thing, people have not. The people are only designing the microstrip, but microstrip has inherent losses. But with this microstrip, how can we get the efficient antenna? It is not possible to get the efficient antenna. The efficiency. The main thing here is that the energy harvesting. Main thing is the efficiency. That is the main thing.
okay, okay.
So efficiency, if we want to get efficiency, then this microstrip patch antenna will not be good one. This type of antenna will not be good one. So this is the main thing. We need to have different technology, not this technology. Maybe direct unit antenna, maybe SRW, or maybe some other type of um, maybe mathematical type of thing, maybe this type of thing. But microstrip, I see lot. I was reading that a lot of people are only designing with normal microstrip patch antenna with for energy harvesting, but the efficiency are very low. They are not getting anything, and they are publishing paper. But this technology will be a good one. But the literature very limited paper. There's no paper there. I mean, very limited paper. This one is the one energy harvesting antenna, and for this energy harvesting antenna, this is the direct unit antenna, and this is the ground plane, and this is the feed line, and this is from China. And for this antenna, there's a two port. This is one port and two port, and this is the direct unit antenna. And the authors say that they are using the energy harvesting application. This type of direct unit antenna they are using for energy harvesting. I think direct unit antenna will be used very good, will have very good for energy harvesting. Conclusion. So in this section, in this lecture, I have discussed different type of SLW structure, direct unit and base antenna. I have discussed the half mode SLW structure, the H plane horn antenna, and corrugated substrate integrated weight based antenna. Also, I discussed different type of direct unit antennas and arrays, and this direct unit antenna arrays will be very good promising candidate for energy harvesting application, because for direct unit antenna we don't have any type of losses. The loss there, we don't have any type of conductor losses, so the efficiency will be very good one. But in literature they are very limited paper. So thank you for listening.
So
Sir,
thank you, Dr. Rana, for your
sir, I have a doubt, sir.
Please go ahead.
Yes.
Uh, Sir, there is any standard materials available for HFSS to simulate the antennas?
Standard
Standard
materials.
material, standard material. Actually, sir, your question is not clear. Your question is not clear to me. Standard material in terms
Sir,
of what?
for there is some YouTube lecturers are available to design the microstrip patch antennas in HFSS software, sir. But
Yeah.
there is an documentation. Any documentation is available to design the procedure for microstrip patch antenna using HFSS software.
Would you like to design microstrip patch antenna with HFS? I mean, microstrip patch antenna in HFSS?
Yes, sir.
There are a lot of literature are there, so you can check in literature. If you need, I can send some training manual to you, so you can use this manual.
Thank you, sir.
Yeah. So any other questions from any participant?
Yes, sir. One question, sir.
Yeah, go ahead.
Sir, what is the radiation pattern, usual radiation pattern of an dielectric resonator antenna?
Normally, the magnetic, like a short magnetic dipole type of radiation pattern. I mean, radiation pattern will be like in the
Is
Z.
it directional or omnidirectional like that?
No, in directional.
Directional. So, sir, since it is energy harvesting, so is it not desirable to harvest energy from all the directions? That is, we
No,
should have the omnidirectional pattern so that we can
no,
harvest energy.
No, so energy harvesting means we want to get energy. So you are saying that from all direction we are getting, but
Hmm.
another important thing is that efficiency is very important for this type of thing. If we want to design one antenna which will get energy from all directions,
Its
it
gain
can
will be
get,
low.
yeah, the efficiency will be very low. So this amount of with this efficiency you cannot get energy harvesting application. For energy harvesting application we need very focused, I mean we need array type of antenna.
Yeah.
If we can like let's say like some sort of, I mean the energy should be very focused energy, then we can send the energy from one point to another point very easily. If we are getting energy from all direction, then it's not possible, I think so.
Okay.
But you can check internet and other.
Because why I'm saying,
Actually,
because this radio frequency will not always come from in a single direction. It may come from the back side of the antenna, left side of the antenna, or
yeah,
the right
Rajesh.
side. Mm.
Yes.
Actually, Mr. Rajesh, I want to comment on this thing. That is actually,
Mm.
if you measure the practical power in the environment, you see the RF scattered RF energy which you will get, that is almost near to minus 5 dBm or below. This is
Yes,
number one.
yes, sir.
Okay, so you will get it. So it is practically not possible, but theoretically, each and we are publishing papers mentioning that we are
Uh,
a antenna, a omnidirectional antenna is capable of receiving energy from all the direction, and it will convert the
uh,
received signal into DC. So this is the theory.
Acha.
Actually, but practically the overall energy which is available in the ambient environment, that is minus 5 dBm or less.
Mm.
So basically, what is being done, say you can create a type of directional antenna which is high gain like DRS, and
Mm.
place the antenna in front of your known tower, in
Mm.
front of your known tower of BTS.
Yes, sir.
Place in the manner that it will focus towards the tower, and
Mm.
that it can intake maximum amount of RF energy from the tower.
Acha. So, sir, we can also use that array of antenna also. Then it will be directional
Yes. Yes.
array of antenna
Yeah,
also.
yeah,
Yeah,
yeah, yeah.
so
Obvious.
for antenna energy harvesting, we need lot of aperture area should be very high. If the aperture area is very high, large, that means more amount of energy will get, and we can use this type of. And one thing is that large area. Another thing is that the focused beam, not like energy from all direction. If the energy is coming from all direction, then the amount of received energy, I mean the electric field will be very less. So you cannot use this type of energy harvesting application. For energy harvesting means we want to get some energy. That's mean we need very large aperture and very focused beam, like a laser type of beam.
Yes, sir.
Yeah.
Okay, sir.
And Mr. Rajesh, let me tell you one thing. The RF energy harvesting research is nowadays in the very nascent stage,
Okay, sir.
because we are not getting a quite appreciable type of voltages
Yes.
from the RF energy. So you
Yes.
are get very less voltage, something 1.2 volt.
Yes, sir.
For
Yes.
example, I am giving you 0.7 volt, 1 volt. So with this kind of lower voltage, what wireless mechanism we can drive? Nothing, na?
Yes, sir.
So, RF energy harvesting is still in the very nascent stage, and the many researches are going on
Yes, sir.
this RF energy harvesting. And
Okay.
actually, energy means solar energy, wind energies are readily available, and using that kind of solar and wind energies, we are getting a lot of power we can generate. But using RF energy harvesting, hardly you can get 1 volt, 1.2, 2 volt, 3 volt like that.
Yes, sir. That's
Yes.
So
why
it is in the nascent stage.
yes, sir. That is why, sir, it is used only for powering small electronic devices, sir. Very small
Yeah,
IoT devices.
all.
But I think
Okay.
within maybe, I was reading one paper. In that paper they are saying within 10 years this for 6G communication, the transfer of
Yeah,
energy will
yeah,
mature, because the
yeah,
people still are
yeah.
doing research, but there's no such devices up there because of efficiency issue.
Yeah.
Yes. Yes, sir. Okay, sir. Thank you very much.
So, Mr. Rajesh, I think that your query is now clarified.
Yes, sir. Yes, sir. Definitely, sir. Thank you, sir.
Thank you. So, any participant, is there any other question?
Excuse me, sir. Dr. Tarun Kumar Das from Kolkata. I want to ask
Yeah.
our speaker, sir, that you have claimed that the microstrip will give us very lossless design. But I know that if I use some dielectric material with substrate material with high dielectric constant like RT Duroid or Rogers, then probably we can get some efficient result regarding the efficiency and gain. And also one thing, sir, for microstrip structure, the flexibility is more. That means if I want to reduce the overall size of the antenna, then different type of fractal geometry that can be easily implemented on microstrip structure. Probably that may be slightly difficult for DRA, if I am not wrong. Yeah, would you please comment on this, whether I am correct or not?
Yeah, you are correct. So this one, this is actually you are correct that because dielectric resonator antenna has high profile, that is the only disadvantage is there. But the problem is that above 30 GHz frequency. So let's say I'm designing one antenna at let's say the frequencies, let's say 5.2 or 3.5, then this type of antenna is very good one. But when I'm trying to design one antenna, let's say 30 GHz, 40 GHz, 50 GHz, then the microstrip antenna will not be good one
Yeah,
because
I got.
microstrip antenna has a significant losses are there.
Yes, I got
Like
your point. So for higher
So,
higher like yeah sir, going on, moving on, sir. Audible, sir, go ahead.
yeah, actually, sir, well, we have only 5 minutes left, and we cannot take any more questions from any other participant. Yeah, please go ahead. Tell me. Any other questions?
No, sir, just
Sir,
that was a
I
query
have
from my side. Okay, sir.
Any other questions from any
sir, I
participant?
have one query.
Yeah.
Sir, the question related to that the design of SIW structure. So in this design, whether we have to insert a metal pin in that via or it is a air-filled gap between this via. Because in most of the literature, I can only
okay,
find a air gap
yeah,
between these two vias. But
yeah, I got
whether
it. I got your yeah, I got your point. So the thing is that the SLU structure should have some metal. So if we use ARVR, then I mean around the ARVR we should have some metal coating. Then air is okay. We need to have some metal coating because the wave cannot penetrate it, maybe the skin depth of the I mean skin depth of normal conductor is very small, maybe 0.001. So one small coating will be there for normal for normal for normal air gap. There should have some coating, metal coating. Then it is okay. If there's no metal coating, then it not work.
Okay. Okay. So, thank
okay,
you,
thank
Dr.
you.
Rana, for your valuable presentation. So right now we cannot take any other questions from the participants. So now I am ending the session of Dr. Biswarup Rana over here, and our next session will be starting within 5 minutes. And all the participants are requested to do come back with the same link after 5 minutes. Thank you all, and thank you very much.
Thank you, sir.
Thank you, sir.